Okay. Yeah. So last class we saw analog filter designing, the IR filter designing, given the specifications like what are the ripples in the pass band, stop band, and what are the pass band frequencies, stop band frequency, etc. So if we know these criteria or specifications of filter, we can easily design an analog filter. And the analog filter transfer function HS can be easily converted to from S to Z using a suitable transformation. We saw all these things last class. So today we shall see a little more specifically by given specification of a FIR filter, how will we go for FIR filter designing? Okay. So given the specifications like say ripples or maximum attenuation, etc. So we shall do that. So now we'll be going to presentation mode. I'll turn off the video. Yeah. Delta P is the ripple. And delta S is the stop band ripple. And the stop band frequency is omega P and omega S are the stop band pass band and stop band frequencies. And 1 by A is the attenuation, or A is the attenuation and 1 by A is the gain in the stop band. So here it is indicated that you have a 60 dB, 60 dB attenuation, which means that the selection of window should be such that you get 60 dB attenuation. Okay. Now, okay. So we already saw these things. And when we go for Butterworth filter designing, it is 1 by 1 plus omega by omega c whole raised to 2n, where capital N is the order. And okay, we saw that Chebyshev filters, there are two types, Chebyshev 1 and Chebyshev 2. All these things we saw. I think I didn't share the video, right? I will share it today. Okay, now coming to FIR filter designing. Suppose you want to design FIR filter. We have already seen how a FIR filter is designed, right? Given a cutoff frequency omega c, an ideal filter like this, and suppose omega c is from 0 to pi, the normalized frequency is considered as 0 to 1. So omega c normalized, which you represent as this, maybe 0.5 if this is in the middle. So given omega c, this response in the frequency domain, which you call desired response, e raised to omega, is 1 or 0, or if you consider negative frequency also, minus omega c less than omega less than omega c. So between this minus omega c and plus omega c, you have negative region also from minus omega c to omega c. Now, if this is the case, ht e raised to omega is 1 and 0 else. 0 else. If this is the case, you know how to design it. You take the inverse transform. If this is representation is this discrete time Fourier transform, so you take inverse discrete time Fourier transform. And normally you will have samples in this, say m samples. So in that case, you take IDFT, and whatever you are getting will be a response which extends. So you take a window in the time domain. The window can be, I told that a window can be a rectangular window. It can be another shape like a hamming, etc. So we shall see in more specifically what are these Hamming window, black band window, etc. And also, if given the specifications as mentioned here, if the filter design criteria are given like this, as in this case, how to design an FAR filter. Okay, so coming. So suppose that you have a filter to be designed. You have some ripples here, and in the pass band as well as in the stop band. This is pass band, and you have frequencies omega p stop band pass band frequency and omega s the stop band frequency, and this extends from 0 to pi. This magnitude, let it be 1 plus delta p pass band ripple and 1 minus delta p, and in the middle you have the value 1, which is the passing value. If these are the cases, you're given these specifications, how will you design your FAR filter? That's the question. Now, you can see that 1 plus delta p and 1 minus delta p, these are the ripple values. And here you have delta s, the ripple in the stop band. So how will you proceed with the FAR filter design? First of all, if you want to design an FAR filter, you need to know what is omega c. You know that omega c doesn't come like this. It will have some maybe something like this, and here you have the omega p and omega s as well as some ripples. So even though your ideal case is like this, your practical implementation will be something like this. Now, given this values, suppose omega p and omega s are given. Omega p and omega s are given. How do you find omega c? Normally, omega c can be taken as average of omega p and omega s. So suppose that you are asked to design an FAR filter with minimum minus 60 dB or 60 dB attenuation. In stop band with, say, pass band frequency, normalized pass band frequency or pass band frequency. Omega p equal to, say, 1000 radians per second, and say stop band angular frequency equal to, say, 2000. These are some values which I am giving. This may not be ideal for some design, but let us assume like this. And suppose you have some sampling frequency. Sampling frequency is given to be, say, angular. You can find angular sampling frequency. So let it be, say, 8 kilohertz. Sampling frequency is 8 kilohertz. So given these specifications, how will you start designing a FAR filter? So it is given that your sampling frequency is 8 kilohertz. So 0 to 2 pi, you have 0 to 2 pi. So 2 pi corresponds to basically Fs, or basically omega s, because you are considering angular frequency. So omega s is basically 2 pi fs, is 2 pi into 8000 hertz, 16,000 pi. Okay. This is the 16,000 pi radians per second. Radians per second. This is the omega s. And what is omega p? It is 1000 radians per second. So basically your omega p, which is, if you consider this as response from 0 to 1, these are normalized. So you have to divide everything by omega s. So omega p normalized, let us write it as a norm. Basically omega p will be normalized value. You may be given omega p as 0.25 or omega s as 0.3, which represent that in your pass band, it starts from 0.25 to 0.3 and the complete thing is to 1. So if it is not like given like that and it is given like 1000, 2000 like this, then you have to find the normalized frequencies, which are basically the omega p itself. So we have to find that will be omega p normalized will be 1000 by omega s. Omega s is 16,000 pi. You find the value, that will be the some fraction 0.35, whatever it is. Similarly, omega s is in the stop band, you have the frequency. The frequency is given to be 2000 radians per second. So actual normalized value will be omega s divided by omega s. Omega s is stop band. So our sampling frequency is also s. We shall write it as capital S. Then basically it is 2000 divided by 16,000 pi. So we'll get another value, say 0.7. So these values, if you get these values, you can find what is omega c, which is the average of this 0.35 plus 0.7 by 2. You get the omega c. So you will fix it as omega c like this. The cutoff frequency is omega c. You design it as an ideal filter with omega c equal to this value. Now you are given that you have a 60 dB attenuation. What is 60 dB attenuation? Depending on what kind of filter you use, you'll get attenuation in stop band. For example, I told that we have different windows, right? For example, if you take a window like this window is used to once you take the once you fix this filter omega, and if you take the inverse DFT, you get a response which may be extending to a large value. So then you take a window over here that makes your approximation. So this window can be of any shape. It can be a rectangular window, and it can be a Hanning or Hamming window, as we have discussed last class. Hanning windows are basically raised cosine functions. Raised cosine functions. For example, window of Hanning window will be Hanning window. Window is basically 0.5 plus 0.5 cos 2 pi n by m. And basically you can see that this can be written as 0.5 into 1 plus cos 2 pi n by m also. This is 1 plus cos 2 theta. So this can be written, this is basically 1 plus cos 2 theta by 2. So you can convert it in terms of cos square theta also. So basically it is a function which is cosine square, or it's a raised, you can also call it as raised cosine function with twice the frequency that is under consideration. What do you call it? Raised cosine. You have zero point 0.5 plus 0.5 cos. This is a cosine function, and you have a DC term. So a DC term basically raises your function. So if this is the window that you use, you call it Hanning window. And if you have some other functions, or if you change the function a little bit, say if your omega n is 0.46, you decrease this by 0.04 and this by 0.4 goes to pi n by m. In that case, this becomes Hamming window. You may wonder what happened when you change these values. A lot of change happened in the frequency response. So you can see that frequency response of this filter, Hanning window, if it is, it has some ripples here. So if you change these values to 0.45 and 0.54, this attenuation goes a little bit lower. That is, your stop band attenuation is larger. You have more attenuation when you have Hamming window. And if you are using, say, rectangular window, it may be even lower than this. We may have some response like this, which may start attenuation from this point itself, which is not disable. Our desired response is like this, ideal response, and our designed response should almost look like this or more closer to this with some attenuation in the stop band. And so if you design using this Hamming window, you make these changes. When you make these changes, you see that there is a lot of attenuation, more attenuation happening in the stop band. While if you change this omega n, say to even this 0.46, you make some small changes. This 0.5, this may be 0.442. Then like remember the exact value. There's some values. Then cos 2 pi n by m. Then some small value with twice the frequency, cos 4 pi n by m. If you change these values like this, you get very high attenuation in the stop band. It can go to say up to minus 60 dB. And while this may be say minus 50 dB for Hamming m, while for Hanning, this can be above that, minus 40 dB or something. So like this, if you want to design with more attenuation in the pass band, you go for this kind of windows, which you call, this window is called Blackman 2-key window. Blackman, you can call it Blackman window. So this kind of window have more attenuation in the stop band, say up to minus 60 dB. So in our problem, we can see that the attenuation is given to be 60 dB. So if you want such attenuation, you have to go for Blackman filter design. And suppose this was say response at this was say minus 50 dB, then you can go for Hamming design. So in that case, you will utilize this equation. So let us assume that it is minus 50 dB, then you can go for the this small designing. In that case, you will have 0.5 plus 0.5 cos 2 pi n by m. Now, what is this capital M? capital M depends on, suppose you have, say, window, you have selected Hamming window. You know that the response is like this. Response is like this. You have some attenuation here. So the main lobe, you call it main lobe, and this as main lobe or major lobe, and these as minor lobes. These are ripples, and these are the called major lobes and minor lobes. These are all called minor lobes. So major lobe decides the transition bandwidth, that is omega p minus omega s. This is omega p, pass band, stop band. Omega p minus omega s is the major lobe width. So for each of this window, you have major lobe width. So for Hamming window, it is approximately 8 pi by m. So you know that omega p minus omega s. In our case, omega p minus omega s is the difference basically. So omega s minus omega s is larger. So 0.7 minus 0.35, which is 0.35. Okay. So if this is to be 0.35, you have to do the this is in terms of pi. So otherwise you can remove this pi or you put pi here. From this you can get what is the m. So in this case m will be 8 by 0.35. So you'll get a suitable value to approximate to the nearest integer. So suppose that it is what will be this value, 8 by 0.35. Right. Okay, let us approximate it to 3. Not 3, 8 into 8 by 0.377 by 2. 0.7. Okay, approximately 23. So capital M is 23. So once you get M as 23, it's basically going to become your order. Okay, it will have relation to your order. So so M is obtained, and omega c you have already obtained. It is 0.35 plus 0.7 by 2. So that value is also you have obtained. So omega c is obtained. From this you got what is the order required, capital M. So you have from 0 to values from 0 to m minus 1. So if you take the inverse DFT of this say samples in the frequency, you get a response HN, and you put a window. The window is basically maybe extending from minus m to m, so that you have to shift from 0 to you have to shift it to the positive direction because you want the filter to be causal. So for the system to be causal, you should have the signal or HN only in the positive side. So to shift that, you do the shifting in the window also. So shift the window from 0 to m and then multiply it. Then what you are going to get is the approximation of the filter transform, which will satisfy all these criteria which are given. So I think we shall have a tutorial sessions which contain basically problems from FAR filter and IAR filter with these specific filter specifications. Yeah, I think with this we can stop today's class. So today what we have seen is FAR filter designing. How FAR filter is designed? We are given the specifications like pass band and stop band frequencies and ripples. You can find what is the order required, and you can find the cutoff frequency, and from that you can design the HN using a suitable window which suits your need. That is, the stop band attenuation should be satisfied, and major lobe width is taken such that the order is we take the suitable order such that the major lobe or the transition frequencies are taken care of. And usually when you want an attenuation stop band, say up to minus 450 dB, we won't go for Blackman window. We'll go for Hamming window, because if you select Blackman window, you will require larger order filter for the same design. So we'll always go for optimum filter design. Okay. So we shall do more problems as tutorial in the next session by including problems from FAR and IR filter design. Okay. So with that, we shall stop. I will stop recording now.